So suppose we have a system of congruences. We can always rewrite this as another system of probably more congruences with coprime moduli, where the moduli are prime powers. As long as the system is consistent, there will be a solution X, and any two solutions are congruent mod the product. But will X solve the original system? So let's consider that first congruence. By assumption, this produces some of the congruences, say, as long as X solves these congruences, X will solve the original, and it doesn't matter if X solves additional congruences. Consequently, our solution to these congruences will solve the first congruence. By a similar argument, X must solve all the other congruences, so this will be a solution to the Chinese remainder problem. Now, we should go for the details. In the case where the moduli are coprime, the solution is unique modulo the product of the moduli. If the moduli aren't coprime, notice that the new coprime moduli are prime powers. Necessarily, these will include PI-NI, the highest prime power factor of any of the moduli. This means the product will be the least common multiple of the original moduli. Now, even though we've found a solution, remember, we should always look for improvements. One difficulty is deconstructing the system of congruences into a sequence of congruences with coprime moduli. We then need to verify that the system is consistent. And in particular, if we find the new system has a pair of congruences with different congruents over the same moduli, then no solution exists. Is there an easier way to determine this that doesn't require us finding the entire system first? Well, let's start with a system of just two congruences. Now, if the greatest common divisor is 1, then the standard Chinese remainder theorem applies, and we are guaranteed to find a solution. So we'll assume the greatest common divisor is some other number d, and that means we can write n1 as d times something, and n2 as d times something. So suppose our greatest common divisor is d, and that x is a solution to the system, so we know the difference is something times dq1, and the difference is something times dq2. So if we find the difference, we get, consequently, A2 is congruent to A1 mod D. Putting this all together, this means that if our system of congruences has a solution, then the congruents have to be congruent mod the greatest common divisor of the moduli. Now remember, consider the contrapositive. If this doesn't happen, then no solution exists. And a useful strategy for familiarizing yourself with mathematics is check for consistency. While we assume that our greatest common divisor was d, if the moduli are coprime, that greatest common divisor is 1, and, well, any two numbers are congruent mod 1. Another useful strategy is to always ask, is it enough? This only establishes a necessary condition for consistency and thus solvability. But is it sufficient? So let's think about that. So again, if n is d times something, then x congruent to a1 mod n1 can be split into x congruent to a1 mod q1 and x congruent to a1 mod d. Because again, we can split the modulus into a factorization and get two congruences. Likewise, since n2 is d times something, then x congruent to a2 mod n2 can be split into two congruences. Since the greatest common divisor of q1 and q2 is 1, these can be further split into congruences mod distinct prime powers. And since a2 is congruent to a1 mod d, then whenever d is split into congruences mod distinct prime powers, the system will automatically be consistent. consequently, we have our theorem that the system of congruences has a unique solution mod the least common multiple of the congruences, provided that the congruents themselves are pairwise congruent mod the greatest common divisor of their respective moduli. Now, that's a bit of a mouthful, so it helps to have a concrete example. So let's consider this system. We note that the greatest common divisor of the first two moduli is 6. The greatest common divisor of the first and third moduli, well, they're coprime, and the greatest common divisor of the last two are also 1. So since A is congruent to B mod 1 for any values A and B, we only have to check to see if the first two congruents are congruent mod the greatest common divisor 6. But we find that 7 is congruent to 1 mod 6, but 11 is congruent to 5 mod 6, so this system has no solution. Now, take another one. So our greatest common divisor of the first two is 7, so we check to see if 17 is congruent to 3 mod 7, which is true. Also, the greatest common divisor of the second and third is 5, so we check to see if 3 is congruent to 18 mod 5, which is also true. And finally, the greatest common divisor of the first and third modulus is 1, and 17 congruent to 18 mod 1 is automatically true. And so this means we can rewrite our system of congruences. So 98 is 2 times 7 squared, so we get 35 is 5 times 7, so we have, and 25 is 5 squared, so we just keep that. And note that we have non-coprime moduli, but if x is congruent to 17 mod 49, it automatically includes x congruent to 3 mod 7, so this latter congruence is redundant. Likewise, x being congruent to 18 mod 25 automatically includes x congruent to 3 mod 5, so we can ignore this congruence as well. And so we can solve our system of congruences, which gives us our least positive solution.